2.7 Part 3 Notes. In this part of the notes, we're going to look at translations of functions. So moving functions up, down, left, and right. We're going to start with vertical translations. So a vertical translation looks like taking a constant, in this case k, and adding it to the end of a function or subtracting it. So if we have our function and we add k to the end, that would move it up k units on a graph. If we subtract k off of the function, then what that does is it moves it down k units. In this first example, we are graphing the absolute value of x minus 4. So remember what our parent function looks like. Just f of x is this red function. It goes through the origin, 0, 0. But if we're going to move this graph down 4, then we take all of our points and we move the output down 4. We subtract 4. So I end up with these blue points in this blue graph. Here's another visual. Our blue graph is the original graph, and then the pinkish red graph we've added 2, so we've moved every point up 2 units. And the green graph, we have moved it down 3, so we've subtracted 3 off of each of the y coordinates of the points from the blue graph. Next, we have horizontal translations. Now make sure that you write this really clearly in your notes because it's a little counterintuitive. So if we have f of x minus h, so if we have x minus h in our function, then what that does is it moves our graph to the right h units. You probably would have assumed that it would be to the left since it's a minus h, but it's backwards. It's counter of what you probably would assume. Likewise, if we have x plus h in our function, then we're moving our graph to the left h units. In this example, we're looking at the graph of g of x, which is absolute value of x minus 4. So this time that minus 4 is inside of the absolute value bars. So what that means is that we're going to move everything to the right 4. You can see that the blue graph has been shifted right 4 units from the red graph. Here's another visual. The blue graph is my original graph. So if I have f of x plus 2, the red graph, it's moving everything to the left 2. F of x minus 3, the green graph, is moving everything to the right 3. For this example, we're graphing f of x, which is negative, absolute value of x plus 3, and then a plus 1. So if I was going to ask you to do this, you're looking for the different transformations that's going on in this function, and we have 3 of them this time. First of all, you should notice that we have a negative out front, which means we're going to reflect across the x-axis. So instead of opening up like a V, like our absolute value graphs normally do, it's opening down. Next, we have x plus 3 inside the absolute values, so that's going to be a shift left 3. So we're moving all of our points left 3. Specifically, think about taking this point right here at the origin. Remember, your parent function looks like this. And moving it left 3. 1, 2, 3. And then our third transformation is up 1. So we're going to take that point that we just moved 3 to the left and move it up 1. And that's how we get that new point. For this next example, I want you to think of the transformations going on here. So first of all, we should talk about probably what the parent function is. This isn't an absolute value function. This is a quadratic. So it's a U-shaped graph called a parabola. Pause your video right now and write down the 3 transformations that are going on in this function. You should have found these 3 transformations. First of all, the negative out front means that we're reflecting across the x-axis. So instead of my graph opening up, I'm going to have a graph that opens down. Next, we have a shrink by 1/2. A shrink means that our graph is going to get wider. So instead of having the normal width of the parent function, we're going to have something that's just a little bit wider. And then up 4. So here's what our graph would look like. It's facing down because it's been reflected. It's moved up 4 units. See, the vertex has moved from the origin up 4 units. And it's slightly wider. I know it's kind of hard to see that, but let me tell you how we can kind of look for it on a graph. Okay, I know it's a little bit hard to see since we don't have the grid marks in the back, but this red function is would be without any shrink or stretch. And I know that because when I go from the vertex to the next point, it's just over 1 box, down 1 full box. Over 1 box, down 1 full box. That would have no shrink or stretch. But the blue one goes over 1 full box and then down half a box. Over 1 full box, down half of a box. So that's why I know that there was a shrink of 1/2, because it's just going down half of the box. If we look at something like this green function, we can tell that it has a stretch of 3 because we can go over 1 box and then down 1, 2, 3 boxes on both sides. So over 1 box and then down 1, 2, 3 to make it to that next point. And so since this is 3 boxes right here, that would have a stretch of 3. Your other option when you're graphing, you could just make a table. Anytime I have you graph any function, you can always make a table, plug in values for x, see what you get out, and you'll have ordered pairs that you can then graph. Here's a summary of the graphing techniques that we've talked about. This may be a good thing to put in your notes. Kind of just diagrams everything and points to each of our transformations and tells what it does.